Great, cool. Oh, didn't erase this. What the hell kind of chart have they been using? So, first things first, we have homework due today, do we not? 5.1, 5.2, and 5.3.
No.
Yes. Yes. 3 sections of homework. These ones are worth the most of the whole semester. Okay, all right. Questions on the homework. So we're only have 5.1 to worry about today. Questions? 37. Okay, who has 37? What is it?
The function f is actually 1
Okay, so you're supposed to find the derivative of the inverse, I assume?
Yeah.
So in 37, we're given that f of x is equal to 2x cubed plus 3x squared plus 7x plus 4. We're given that a is equal to 3. And
I have issues.
okay, so maybe that's why you can't. So let's go through it anyway, because it's like you can't get the damn answer. Yeah, you wrote the wrong. It's not the wrong part. So the question was to find the derivative of the inverse at 4, which is a. Okay.
One after was 3.
So yeah. So what was the first step? Find derivative. What is that? Second step. Find the inverse at 4, which will mean we need to set 4 equals to 2x cubed plus 3x squared plus 7x plus 4, which in other words, 0 is equal to 2x cubed plus 3x plus 7x. So what's the solution here? 0. All right, x equals 0, that's the obvious one. It's a cubic, so we know it's 1 to 1, so it will, well, you can check that it's 1 to 1. You factor out the x and then you factor the quadratic and then blah, blah. It's not necessarily 1 to 1 being a cubic, so step 3, let's do it over here. Let's use our formula. So we know that f inverse derivative at 4 is just 1 over f prime of what value? 0. So that's just 1 over, now we go to f prime when you plug in 0. So that's 6 times 0 squared plus 6 times 0 plus 7. So it's 1/7. Other questions? You have another? Yeah.
Okay, so when you have x is equal to 0, why did you only pick that one? You could find another x value.
Are you sure?
Well, if you factor x
If you
out,
say x, here you get 2x squared plus 3x plus 7.
and then set each part equal to 0.
Right, so if this guy equals to 0, what would your x be? What would x be? Huh? X would be equal to, that's right, quadratic formula, minus b plus or minus the square root of b squared. So it's 9 minus 4 times a times c all over 2 times a. Now you see this guy here underneath the radical, it's negative. There's no real solution, so there's no x that solves that. The only one is going to be 0. Right, so they'll have to, for this, like I said, to work out this guy, the inverse would only exist if you're 1 to 1. There shouldn't be 2 solutions. Right, so if you find there are 2 solutions, but you better check the question, make sure they didn't give you a restriction. Like sometimes they'll give you a restriction, but for this to even work out, it has to be a 1-to-1 function. There should be only one solution. So if you see the obvious solution, don't worry about looking for anything else. There's only one. Other questions? Yes.
46.
46.
I have it.
It's the one with the inverse of sine.
The sine one. A couple people asked me this today. So it says one part was to show sine x is not 1 to 1. And the other part said show sine x, if we restrict it between minus pi over 2 to pi over 2, is 1 to 1. And then the third part was to find a formula for the derivative of the inverse of function. So they said this was f of x, and they asked for the derivative basically of sine inverse of x. Or
Yes, do so.
so dx arc sine x. Right. There's alternate notation for the same thing, right? So sine inverse and arc sine. They're the same thing. So if you see one versus the other. Okay, so how to show that sine x is not 1 to 1? Yeah.
You can graph it.
You can graph it. That's one way. So the first bullet point is if you graph sine, you know it looks like this. And it goes backward like that. And this continues forever, right? The same pattern. So that's 0. This would be a pi over 2, pi, 3 pi over 2, 2 pi. Right? So how do we know this is not 1 to 1? Right, it doesn't pass the horizontal line test. You draw a horizontal line, I can literally cut it in an infinite number of places. Right, so it does not pass horizontal line test. Okay, so
How else would you know if it's not 1 to 1 besides the horizontal line test?
the formula I gave you, remember we said 1 to 1 means if f of x equals f of y, then x must be equal to y. Right? I did write that down at some point. Right, so all you have to do is prove that if sine x, you can have sine x equal to sine y, but x not equal to y, and that's pretty easy to show. For example, sine of pi is equal to sine of 2 pi, but obviously pi not equal to 2 pi. Right? So I have two values where the outputs are the same, but the inputs are different, meaning it's not 1 to 1. Okay, so the second part is, what if we restricted it? So sine is doing this guy, this thing here. Pi over 2 is here. Minus pi over 2 is here. And what they basically said is we're going to restrict the function. We're going to start here, and we're going to end here, and essentially forget about everything else. Right, so here they put in a restriction. Right? Now is it 1 to 1? Well, yeah. Now you'll pass the horizontal line test. Any horizontal line will only touch this once. So pass this horizontal line test. Right? So you could also prove it by the other way. The thing is, for sine to actually repeat its value, you'd have to travel a distance of more than pi. But here, the distance is pi. You'll never get to a point where you can repeat a value. So this means now it's 1 to 1 with the restriction. So those parts weren't bad. Really just graphing it and showing the horizontal line test. Whether or not it works is good enough. Now for the last part. The last part is the nice part. How do you derive the derivative of sine inverse?
First find that prime.
Okay, so we have f of x. It's the same thing we've been doing, right? So this is sine x. So step 1 is to find f prime. Cosine x. Second step is to find f inverse. But they didn't give us a point, so you just say f inverse of x in general, in which case we don't really know how it's defined, so we just literally write this is just sine inverse of x, whatever the value of the inverse is. 3, you plug into the formula. The derivative of the inverse, which means I'm taking the derivative of sine inverse, is just 1 over f prime of the inverse function, which is this. But what is f prime? It's cosine. So this is just 1 over cosine of sine inverse. But we're not done. You can actually simplify that. Okay, so does anyone know how to simplify that? You can't bring the sign to the top. This does not mean 1 over, by the way. This is not the same as this. On top of that, it's inside the angle of a cosine. You can't like just take it out. So that wouldn't work anyway. Right? This is one of the reasons for the alternate notation where people write this as arc sine. Right? They write that so that people don't get confused and think this is 1 over, because it's not 1 over. What is 1 over sine? It's cosecant, which is not this function. Right? So this is just a notation. It comes from the inverse notation. So it's not 1 over. Don't make that mistake. So how do you simplify this? How did you get that? Were you in the tutoring center today?
Not yet.
No, someone who was not in the tutoring center. Someone who I did not tell them the answer. I'm trying to take credit for my hard work. Any ideas?
You're
Yeah?
asking how to simplify, right?
Simplify, yeah.
1 over cosine is a secant, right? Could
Yeah.
you write it as secant sine inverse of f?
You could? How would that help though?
Do you have to bring an identity?
I don't want any trig functions. You don't really need identities. SOHCAHTOA you can use.
Oh.
Yeah, so stuff like this you dealt with in pre-calc a whole 2 semesters ago. Okay, so the trick is the following. You call sine inverse something, like an angle, call it theta. Which by the properties of our inverse function, we can get that x is equal to sine theta, right? Just bring the inverse over. The x you can think of as x over 1. Does anyone see where I'm going with this?
Yeah.
What's the next step then?
X is opposite.
Opposite over hypotenuse, right? Which means this guy I can form a triangle on.
Yes.
Where this is opposite over hypotenuse. What is this side?
X square root of x, square root of 1 square minus x.
1 squared minus x squared, right? Pythagoras' theorem. So, in other words, cosine of sine inverse is just cosine of theta, right? Because sine inverse is theta. From this triangle, what's cosine of theta?
Adjacent over hypotenuse.
Right, adjacent over hypotenuse, so it's 1 minus x squared. So this means the derivative of sine inverse is equal to 1 over cosine of sine inverse, which is 1 over the radical of 1 minus x squared. This is actually a rule. So if you look in the cover of your calculus textbooks, it would say that's the derivative of sine inverse. How did they figure it out? This is how they figured it out. Right? And you can do a similar manipulation with cosine inverse, tangent inverse, secant inverse. You sort of do this trick, and then when you get to this point, you're going to have a trig function and an inverse trig, and this is how you get rid of the trig function. That's that for that question. So they had you derive the formula for sine inverse. The derivative of sine inverse. Or the derivative of arc sine. Yes, it's something you have to memorize. Or you could do this on the test if you want, but I wouldn't recommend it. Just remember it. The derivative of sine inverse and the derivative of tan inverse shows up all the time. So the derivative of tangent inverse would be 1 over 1 plus x squared. Which, by the way, you should also know that once you know the derivative, you also know an integral formula, right? The integral of this guy would give you inverse sine. Whereas the integral of this guy, which we'll be seeing tons of in the near future, is tan inverse, or arc tangent. Other questions? Yeah. 43. What is 43?
Equal integral of radical 1 plus c cubed dt. Find f inverse of the inverse of the derivative at 0.
Okay. So I still have my marker from the last time. Let us go to our prerequisite. Oh, do I want to get rid of this? Maybe not. I'll leave it there for a day. So right now we have a substitute prerequisites corner. Remind you of some stuff that you should remember from top 1. Called the fundamental theorem of calculus. Right. There are 2 parts to it, as you might recall, right? So there's, I'm not going to go through there's this continuous and blah, blah, blah. Forget all the words, right? There are 2 equations that you worry about, right? So there's one that says the integral from a to b of f of x dx is equal to big F of b minus big F of a, right? Where f of x is the antiderivative of f of x, right? There's also a second one. Anyone remembers what the second one says? Not. So the second one says it's possible to define a function in terms of an integral, where there's a constant here and there's an x there, of some function of t dt. And if that's the case, then you can actually find the derivative of this function. And what's going to be the derivative? The function evaluated where? At x. Fast forward to calculus 2. What's step 1? Find the derivative. We have a function that's defined in terms of an integral where the lower limit is a constant, the upper limit is x. What is the derivative?
1 plus x.
Radical of 1 plus x cubed. Step 2. You need to find the inverse at 0. Which means, what do I need to do? How do you find the inverse at 0? You set which function equal to 0? This equal to 0, right? So 3 to x of the radical of 1 plus t cubed dt equals 0. Now, how do you make that equal to 0 depending on x? X has to be 3, right? because that's another thing that we learned in Calc 1. The integral from one point to the same point of any function is always 0, right? The area under the curve from a to a is nothing, right? So if you want to make sure your integral is 0, make the upper limit the same as the lower limit, right? So if the only thing I can manipulate here is x, there's only one value to pick, whatever the lower limit is. X equals 3 has to be the solution we're looking for. Go down to 3. So here's the formula. So when you want the derivative at 0, it's going to be 1 over f prime evaluated where? At 3. The answer to step 2. So this is just going to be 1 over what's f prime? Just this guy. So I'm just going to go here, and I'm going to plug in 3 for x. So 1 over radical 28 will be the answer. But here they're checking if you remember the fundamental theorem of calculus. Here they're checking if you remember how to make an integral 0 with the limits. Other questions? How much time do we have? One more if there's a question. Make it good. No?
39. X equals 3 plus x squared plus tangent pi x divided by 2.
That's 3 plus x squared plus
Tangent pi x over 2.
pi x over 2. Like that?
Well, yeah, it doesn't matter. That's fine.
Yeah, that's it.
Okay. That's the function?
Within the restriction of negative 1 to 1.
So x is between -1 and 1.
A is 3.
So we want to find the derivative of the inverse at 3. Step 1. What do we do? Find f prime, which is 2x plus secant squared of pi x over 2. Huh? Multiplied by pi over 2. Step 2. Find the inverse at, what did you say it was? A equals what? 3. So find the inverse at 3. So what I'm going to do is I'm going to set the original function equal to 3, which basically means x squared plus tangent of pi x over 2 equals 0. X equals 0. Obvious solution, because that would be 0. Tan of 0 is also 0. So x equals 0 is that one. The restriction makes it 1 to 1. So if you see the obvious solution, don't waste your time looking for anything else. So now we're at the derivative at 3 is just 1 over f prime at 0. So that's 1 over, plug in 0 here, that's 0. What's secant of 0? Secant of 0 is 1, so this secant squared is obviously still 1, so that's just pi over 2. So this gives us 2. Good. So that's it for homework. Pass your homeworks to the front row so I can collect them, and we will move on. Okay, and we are moving on I left you guys with a couple problems to try last time. Hopefully you guys tried them. Without copying from someone, otherwise I have to send the cops after you guys too. See what happened? See what happened? Don't cheat on your homework. I am serious when it comes to that stuff. I'd be like, come on, 911, he's here. So pretty much the only thing left here to do is just a few examples. I introduced log differentiation. Last time we went through 3 steps to find it, and I believe I did the derivative of x to the x. And I left you with an example. What if your y is something like radical x, x plus 1 to the 3 over 2, 2x squared plus 7, 2x squared plus 1 to the 7. And I didn't even try to make that ugly. They can get tons ugly. Okay. But with logs, it's still actually not that bad. It's a lot to write out, but it's simple at the same time. A lot simpler than you would be going through the quotient rule and then have to simplify and factor in your radical half fractional powers and stuff. Okay, so what was the first step in log differentiation? You take the ln of both sides. So ln of y equals ln of this
Mess.
this huge mess.
If you write log, would it be wrong instead of ln?
At this level, yes. Right now, when people write log, they mean log to the base 10, but they don't write it. Well, ln means log to the base e. When you get to higher mathematics, this is the only log you're ever concerned with. So if you're doing like advanced mathematics where you're proving all this crazy, beautiful mind stuff, they'd write log to mean this. But
So we write ln. pretty
yeah,
much.
we want you to write ln at this level. The only people who write this for ln are mathematicians who are like way up there. Like if you're in science or anything, log means base 10 is implied. Okay, so
Break it up by logs.
now you can break this up by the log rules. That's what it's for. So what would happen? So this, radical x is just half power. Let's take a few steps so that everyone can follow. So we had a rule that says we have a log of something divided by something. What does that mean we can do? We can do a subtraction. So you can say log of x to the 1/2, x plus 1 to the 3 over 2, minus 2x squared plus 1 to the 7th. Do that. Already start looking simpler. We don't need a division anymore. Here we have a product, right? Log of something times something. That's just addition, right? So that's x to the 1/2 plus log of x plus 1 to the 3 over 2 minus log of 2x plus 1 to the 7th. We can simplify one more step before continuing, I think. So we still have ln y on this side equals right, so logs turn division into subtraction, they turn multiplication into addition, and they turn powers into what? Products, multiplication. You can bring the powers down in front. So here we have 1/2 ln x plus 3 over 2 ln x plus 1 minus 7 ln 2x squared plus 1. And now we can differentiate. The left side becomes what?
1 over y. Oh, wait, implicit, right.
Implicit, so it's y prime over y, right? That's the general rule. Remember, your y is a function of x. You have to apply the chain rule. What's the derivative of ln x? Just 1 over x. 3 over 2 times derivative of this. 1 over x plus 1. Remember, it's the derivative of this guy over this guy. So the derivative of this is 1 divided by that. Minus 7 times So then your y prime would be just y, which is the original function. If you want to rewrite this whole thing, you can, but I'm not in the mood for that. This is just 1 over 2x plus 3 over 2x plus 1 minus 28x over 2x squared plus 1.
Can we just leave the y on the exams too?
Well, if it's crazy, I mean, if it's simple, you just rewrite it. So that would be the derivative. So it's a few steps to write down, especially when you're not used to it. When you get used to this manipulation, you'll be able to jump from here to here with no trouble. You'll just see, oh, that's a product, I can bring that down. You'll see it in your head the more you practice, right? So, but I just wanted to break it down for those who are unfamiliar. So that would actually be the derivative. What if I said something like y equals, another example, y equals 2 to the x. Log both sides, that's easy. So I get ln y would be x ln 2. So ln y is equal to x ln 2. And so if I differentiate both sides, what do I get?
Y prime y.
Y prime over y. ln 2.
Oh yeah.
Right? ln 2 is just a constant, right? So x times a constant, the derivative is just a constant. This means that y prime is just y times ln 2. In other words, it's 2 to the x ln 2. We're going to come back to formulas like that we can generalize the exponential derivatives. What about something like this?
I think you gave us another one to work on.
I did?
Yeah.
So y equals x squared plus sine x to the x. Okay, what do we do?
Log both sides.
Really? Okay, so we log both sides, and what would happen?
Like log them individually, right?
How are you going to do that?
You're supposed to take the derivative of both sides.
Can you subtract x squared and put it on the y side?
Yeah, but then you do that, and then you log over here, you'd have to log y minus x squared.
So you just take the derivative of both sides.
So here's the thing. Why couldn't I log each part individually?
Because it wouldn't be.
Because we're logging both sides.
Because you have to log the whole side. So if you think you can do it individually, what are you actually saying? You're saying that log of a plus b is equal to log a plus log b? We know that's not true. So you can't just log a sum and then distribute the log. That's not a rule. You have to mind your rules, right? So you can't log individually. So if you're thinking of logging both sides right here, this is what you get. With that plus in there, we don't have a formula to expand that. So logging both sides is not the right first step.
Take the derivative of both sides. Take the derivative of both sides.
How do you derive the last?
How do you take the derivative of both sides?
Well then, don't you have, well then you can have sine x so that x as a different function and it's do that separately and then put that back in.
Yeah, we know that the derivative of a sum is just the sum of the derivatives. So all you do is just figure this guy we know how to differentiate. It's just 2x, right? That's not a problem. So forget that for a second and just work on this guy. Do it one at a time, right? So you go over here and you say something like, let g equals sine x to the x. In the next section, I'm going to show you a shortcut where you actually don't have to break things up. But for now, this is what we can do. We can't log both sides, so just do them individually. So define a new function, call it this, figure out what the derivative of this looks like. So now I'm going to log both sides. Which means ln g is equal to x ln sine x, right? Now if I differentiate both sides, what do I get?
G prime
G prime over G. Differentiate that.
1 over sine x and above x. No, wait.
To get G ln sine x plus xg cos x.
ln sine x
ln sine x.
multiplied by,
Nope.
first,
Plus
yeah, plus x.
x times
xg cos
1 over sine x, 1 over sine x multiplied by cos.
x cos x over sine x.
cosine x over sine x. So this means that g prime is equal to the original function g times ln of sine x plus x. Give me another way to write that.
Tan.
X cotangent.
Cotangent x. Okay, so now we can differentiate that. So this means that my y prime, going back to the original, is going to be equal to what?
2x.
Derivative of this, which is 2x, plus the derivative of this, which I just found.
Sine x.
That's just sine x to the x times
ln sine x.
ln sine x
X cos x.
plus x cotangent x. So I put a problem like this with a plus in the middle because I know I'd catch something. Be careful of those rules. Know the rules, right? You can't distribute an ln across a sum. That's not a rule. Do not assume you can do it. If you could have done it, I would have told you. Do not assume you can do something I don't say you can do. And we'll all be happier. So here, yeah, you see a sum, just break it into two parts, right? You don't need log differentiation for this, but this one you do because the power is a variable, right? That's one of the indicators that you're going to need a log differentiation or something similar. There's another method I can show you, but for that we need the next section, 5.3. So that's what we're going to do now, 5.3. Any questions on this? Can we finish copying it? So we're going to do 5.3. We're going to talk about the natural exponential function. Now this is just the inverse of the natural log function, and I told you some information about it last time. But let's give it its own little spiel. So recall that if you have ln of, what did I say, x, ln of y equals x is the same as saying, remember here, the base is e, but they don't write it. By the definition of a log, what do we get? E to the x equals y. The function e to the x is called the natural exponential function. Why is it called the natural function? In calculus, it's natural, right? We usually call something natural when it's easy to deal with in a certain context because it just shows up on its own. It's natural, you know. Why is it natural? One important rule is that you can derive. Did I tell you this early? Well, here I said, you know, they're inverse. I showed you that last time. Right? E to the x, let me mention it again, is the inverse of ln x. So that means on a graph, ln looks like this. Passes through 1 because the log of 1 is 0. You do this, y equals x. Then the other guy is going to look like this, passing through 1 on this guy. So this is y equals e to the x. This is y equals ln x. E is roughly what value?
2.7.
2.718. Okay, good. So, do I tell you why it's natural now? Okay, so from the graphs, I'm just excited, I just want to get to it. From the graphs, I didn't tell them yet. We see, like I said, we're getting back to limits, so I'm slowly introducing them. The limit as you go to infinity of e to the x equals the limit as you go to negative infinity of e to the x equals. As you go to infinity, it gives us infinity. As we go to negative infinity, it gives us 0. Right. We're going to revisit this and we're going to learn a lot of things by just looking at how limits behave. We'll soon learn that exponential functions grow really fast, a lot faster than polynomials, and we're going to use that fact to our advantage. Let's do another example here with limits. What if I ask you to do this limit? E to the 3x over 2e to the 3x plus e to the minus 3x.
Simplify e to the 3x.
How do you get a half?
Is that the same exponent?
Yes, it's one.
3x and 2.
Can't you back out e to the 3x?
To the 3x and 2 to the 3x.
You mean argument? How do you do it? How do you?
X approaches infinity, isn't the x infinity? So it's like 2 infinity plus.
Yeah, well, how do you know infinity over infinity is a half? Cancel out what?
E to the negative is like 0.
No, but that's negative infinity.
Yeah, so this one's going to 0.
Yeah.
But is he ever actually equal to 0? He's approaching
No.
0.
So that means you ignore it.
Yeah, that counts as
You
0
add 0 basically.
to infinity.
You get super high values of x. That one becomes insignificant.
So as x gets huge, this guy becomes so small that he doesn't matter.
Yeah, you ignore it.
And so you have sort of that over that.
Infinity
That is correct. That is a correct intuition in this case.
This case. Give it to you.
Because we're all doing the same, they're all the same kinds of functions, right? If I was mixing different kinds of functions, you have to be really careful. But yes, eventually when you're doing this, you can use that intuition and it'll be fine. Probably what you would do just starting out though is try to simplify. Remember, this is just 1 over e to the 3x, right? E to the minus 3x. Algebra, right? So this is 1 over e to the 3x. So really what you have here is a complex fraction in disguise. So you can actually simplify it by multiplying by the LCD. So you multiply this by e to the 3x over e to the 3x, and this will, or you divide by e to the 3x over e to the 3x, whichever one you'd like. And this would be something like 1 over 2 plus e to the minus 6x if I divide. I could multiply, but dividing is easy. And now you can see that this guy goes to 0, and you don't have to worry about infinity over infinity, right? So you can divide. And so then that's just that. Right? Remember that thing when you were doing with polynomials, you divide by the highest power of x, top and bottom?
Yeah.
Right? Calc 1. Okay, so yeah, you can do the same thing here. The biggest function, look for the biggest, baddest dude, divide by. Right? That's how you survive the whole limits game. Just find the biggest, baddest dude. right? And we're going to learn that exponentials are growing a lot faster than polynomials. They actually grow a lot faster than logarithms, by the way. So if you're comparing them to polynomials or logs, they're always the biggest, fattest two. We're going to use that later on. But for now, I'll leave you with that, just to think about it. Now do I tell them? Okay. Note, I had to say this because sometimes students forget. Y equals e to the x obeys the exponential rules. i.e., for example, rule 1, if I take e to the x times e to the y, what do I get? X plus y, right? Or if I have e to the x, what else did I tell you? I gave you a bunch of this. Divided by e to the y, that's e to the x minus y. That's another rule. Right, all your log rules, basically. So if you have e to the x and you raise it to another power, what happens? You multiply the powers, etc., etc. One thing I've noticed is when you get experienced enough, you're going to realize, as far as this calculus game is concerned, e to the x and ln x are the easiest functions in all of calculus to do calculus with. They're so easy to integrate and differentiate, and but I find that students often have a lot of trouble with it, and I think it's because they look scary. They're like, oh, what is this? I've never seen it before. They like freak out and they forget. They see e to the x, like, oh my god, and they forget all these rules. Like all the basic rules, they're still the same. It's fine. E is a constant. Just don't worry about it, right? Don't let it scare you. You know? I'll probably put a bunch of problems on your quiz that look scary, and it's like nothing. Just to try to catch you with it. Let's make sure you can actually solve some equations. Solve for x. Then am I going to tell you? Yes, after this I tell you. Okay, so let's say I had e to the x equals e to the x minus 7 equals 5. If you make it too easy. Solve for x. Here about b. What if I said something like ln of x equals 12? Solve for x. Come again?
X equals 35 for the first time.
How'd you get that? 35. What's the first step? You log both sides, right? You want to take the inverse function, right? So you ln both sides. And we learned last time that ln and e, they're inverses, so it sort of cancels. So here you're just left with x minus 7 equals ln 5. Therefore, x is equal to 7 plus ln 5. We're going to need to know how to solve an equation.
But
That's coming up later.
I have a question.
Yes.
What if we put the ex minus 7 and we change it into ex divided by e over 7? Can we do that?
You could. You do the same thing.
But
You
they're
get the
not-
same thing.
I didn't.
I don't know why you're thinking so complicated.
You were trying to trick us.
I'm not trying to trick anyone. Right, so let's say you had e to the x minus 7, and you're like, oh, I'm going to be all fancy because Jhevon's trying to trick me. Aha! Right? And you do that. Now what?
No, I meant like split the ex minus 7 to, ex over e over 7. And then take the e over 7 to the other side, and then ln both
You
sides.
can't do that because there's an. Wait.
No.
Oh, you mean before you log both
Before I
sides?
log it.
Okay. Well, at this point anyway, you just do the subtraction, right? This would be ln of e to the x minus ln of e to the
Right.
7, and then you get the x minus 7 again. But you're saying you would actually have this,
Split into e.
and then you write this. You write this.
Yeah. And then ln both sides.
And then ln both sides. Then what?
Right.
This is just x. This would be what? ln of e to the 7 plus ln of 5. You still get 7 plus ln 5.
No,
Just
and
much
then-
longer, more complicated.
No.
Log both sides, distribute it. X squared is not a problem. Why are you gonna go that? Stop it. Relax. Okay, so what's this? Raise both sides of the exponential, right? To get rid of an e, you ln both sides. To get rid of an ln, you raise both sides of the e power. That cancels, so your x is just e to the 12. Okay, so there are probably a few more homework problems that are more complicated than these, but I just wanted to make sure I threw those basic ideas out there. Now, for the kicker, why is this called the natural exponential number? Because it has pretty much the easiest derivative besides the number 0. No, let's do calculus now. Calculus. With e to the x. What is the derivative of e to the x? Turns out it's itself. You literally do nothing. This is the only non-constant function we know of whose derivative is itself. There's no other function that has this property. No other non-constant function. 0 is the only other function that has this property. And it's just a constant. There's nothing much going on. But e to the x, it's not a constant. It's actually a function that's changing. It's its own derivative. It's pretty natural. Right? It's just like, didn't have to do anything. It's just there. You know? And then you have like ln x, the derivative is 1 over x. It's just, that's so easy. And you're like, I'm so glad we completed the power rule. It always bothered me. Kept me up at night. Okay, so yeah, this you should know. Also what you should know, a nice formula you should know, by the chain rule. Let's say we don't have just x, we have a whole function. Like what is the derivative with respect to x of e to the u, where u is a function of x.
E to the u dx, du dx.
Right, u prime e to the u. Right. So that's how you differentiate a generalized exponential function. Derivative of the power times the original function. And that's it. You can derive this using log differentiation if you want, but it follows by the chain rule from this, and this you can derive using log differentiation if you want. So let's actually do we have any examples? Okay, I said here, give examples. Because they're so easy, I can make them up out in my head. Okay, so example. Find the derivative of e to the x squared plus 7x.
See?
2x plus 7.
Oh, right. Then to the power of the same thing.
Is that okay?
Yeah.
That's not okay. That's missing.
Brackets, parentheses, or whatever.
You have to multiply the whole derivative by the original function. Right?
Same. Yeah.
It's like, you can't scare me. He's like sweat running down his face. It's just trying to puff up his chest. It's like, you can't scare me. What's that?
Whatever.
Sine
Wait.
7 plus x times e to the sine x of negative 6 over 7.
1 over 7 cosine x. times sine x
to the 6 over 7.
to the minus 6 over 7,
Then e to the
I mean e to the
then the whole same thing, right? Sine x. Do not forget your training grasshopper. I can make it look really scary. It's just going to be simple. Just focus on the power. What's the derivative? Well, you use the chain rule because I have an inside function raised to a constant power. Power rule, multiply the derivative of the inside, and then you just put the original function back. E to the radical x plus tangent x.
the derivative individually, right?
What?
1/2 x to the negative 1.
All right, so 1 over 2 radical x is the square derivative of radical x.
So secant square x.
Secant squared x,
Bring everything else.
brackets, times the origin. Okay.
Constant, not a function of x, or it doesn't have x, so it's gonna be 0.
Couldn't scare him, couldn't scare him. He saw it coming a mile away. It's a constant, which you'd be surprised how many people forget that. I've caught a lot of people thinking that the derivative of e is e. No, it's not. E is a constant. Derivative of e to the x is e to the x because of the x. It's a function, right? Without, if there's no variable, it's a constant. This is a constant, pi is a constant. So this to that power is a constant. Derivative is just 0. Don't let it fool you. So, also, well, remember, every time we know a derivative rule, we also know an integral rule. What do you think the integral of e to the x is?
E to the x.
E to the x plus c. That's another rule. Of course, these you have to know. You have to like have these memorized. Pretty much anytime I write something in a box, it means you have to memorize it. So, what if I tried to ask you something like e to the kx dx? K not equals 0 is a constant. Give me a formula for it.
E to the k.
e to the x plus c.
1 over k.
E to the k, that's over k.
It's k times e to the k.
Nope. It's 1 over k e to the kx plus c. How would you figure that out if you didn't know? You can do a u substitution, right? Like u equals kx, which means du would be k dx, which means 1 over k du would be dx. K is not 0, so I can divide by it. So the integral would become 1 over k times the integral of e to the u du. And I know by this rule that the integral of e to the u is just e to the u plus c. And then I replace u. So this is 1 over k e to the kx plus c. Hence we can have a formula that's slightly more complicated, but it's worth just knowing right off the bat. 1 over k e to the kx plus c. Because sometimes I'm there, I'm teaching like Calc 3 or differential equations, and I have like, what's the integral of e to the 5x? And I see them doing this, like chuckle to myself, like, can't you pass that? You should just know that, know this.
It's in a box.
Although sometimes when you're grading, you need a good laugh, because otherwise you're like, why? Why? I told them not to do this. Okay. So let's do some examples. Integral of e to the 3x dx.
1 over 3.
Nothing to do there. Right? So that you shouldn't have to do a u substitution. You just know it's 1 over 3, e to the 3. Did I? Please tell me I did something more complicated. X e to the x squared.
Use substitute.
What do I substitute?
X squared, 2x, bring over
X
to
squared. Du equals 2x dx.
du.
So I have 1/2 du is equal to x dx.
So X and
So it's
dx.
1/2.
So this is pretty much 1/2 du. That replaces the x dx.
E over
And I'm left with e to the x squared, but my x squared is u.
E to the power u.
So that's just e to the u. Whose integral I know is just e to the u. One half e to the x squared plus c. More examples. What about that one?
ln of 1 plus e to the x.
Or
Use
split it,
substitute.
split it. E over
So you
1.
do u
Or no,
substitution.
Use substitute.
U
Plus
substitution.
e.
Yeah.
U equals
1 plus EX.
du equals,
EX.
right, which is what we have here. So the entire integral just becomes 1 over u. Du, whose integral is ln of absolute value u plus c. And so then we have ln 1 plus e to the x plus c. Technically you don't need the absolute values, but hey, just leave them in, be safe. Right, because this is always positive inside. So that's the answer there. More examples. Ha ha. Ah. Ha ha ha. What's that? Dude, you substitute.
Yeah. U equals e to the power. E to the The entire thing?
U equals what?
E to the power x. E to the power square root x is u. Just that.
No.
Yes, for sure. Yeah.
Okay.
And then there's,
What's the derivative of that?
you know.
1 over 2 right
E
to the right
yeah.
x.
Exactly.
Okay.
And then you substitute the square root x underneath with the top thing, you know. Like,
Multiply both sides by a half.
Multiply both sides by a half.
I mean by 2.
Okay, so we have 2 du is equal to 1 over radical x times e to the radical x.
Yeah,
but we can't substitute.
you get 1 over u.
We actually, you can't.
Yeah, then
You can't, it
bring
works.
these to the other side, you know, like divide both sides by, multiply both sides by square root. No. Wolf arrow. Wolf arrow.
Then what?
Multiply by rad x. And then you
No,
can
but-
divide out
So
the
multiply
rad
both
x.
sides by radical x.
No, but
So
two rad
2
x.
radical
No,
x.
but you need the radical x because you need.
We
Yeah, and then you can, once you put it up there,
Yes.
you can divide out the rad x.
No, because you want left
No, we
e
want to substitute the
power.
x with some value.
That is what we do.
So if you bring it to the other side, it's multiplying the top.
I don't hear what you're saying. So what, do we not want to
Our
do
U
this?
is wrong, our U is
Let's just
wrong.
start over.
It could work with this U. It's not how I do it, but I know you have the what?
Would it be radical x? The u?
I would do it just be radical x. Yes. It's not that this couldn't work. It could work. You just have to be better with your algebra to pull it off. I would probably just let it be radical x, in which case du is just
1 over 2 squared.
1 over 2 radical x. X. So I can multiply this by 2. 1 over radical x x. And so now I'm going to go back and I'm going to plug this in. So I have 2 du. And that's going to replace what? This guy. What am I left over with? There's another 2 on top over, what do I have now? E to the u. So now how do I find the antiderivative of
Bring out the
that?
constant again.
I can bring out the constant if I want. Put that at 4. And what is this?
1 over EU, so which is e negative u.
Right, it's e to the minus u du. How do we do that?
4 e negative u.
No.
4 ln.
Minus 4 e to the minus u. Why?
Oh,
That's it. General.
K is minus 1. 1 over k e to the blah, blah, blah. You guys forgot the rule already? There's a constant times the variable here, right? There's a minus 1 times u. K is minus 1. 1 over k is 1 over minus 1. Just minus 1. So it's minus 4 e to the minus u, which is this guy. So that would be that answer. This doesn't involve an exponential, but I think it's a nice one. But let's see if I remember. Was it? Maybe? Was this it? X plus radical x, I think it was. Could we do that? Maybe. I'm having way too much fun. We need to move on. Ideas? How do you do the calc one way?
Well, since they're both at the bottom, you just say x. It's really x minus x to the negative first power plus x to the negative 1/2 power, and then solve from there.
Divide by the highest power.
So you think this is x to the negative 1 power plus x to the negative 1/2 power?
No.
Wow,
That's just pretty.
What did she do there?
Ruin the Minecraft. Split the
Huh?
Matrix.
She gets a 0 the exam.
She gets a 0. That's a blasphemy. That was a blasphemy, right? It sneaks up on you. That's why I had to warn you about it. Why is that a blasphemy?
Because the difference only works if it's product.
Because what this really is x plus radical x, x to the half. All of it is to the minus 1. What she actually did was that, right? So she put the minus 1 here and a minus half here, right? That was distributing a power across a sum.
You're not the one.
Okay?
You're not the
Leave her alone. I've seen a lot of people make that mistake. Don't worry about it. You keep going. Okay. It's better you find out about the mistake now than you find out on a test. Like, oh, I didn't know I could do that.
No idea.
Yes?
Can you split it up into 1 over x the integral of 1 over x plus the integral of 1 over radical.
Nope. Also a big algebra mistake. You cannot split a fraction across the denominator.
No idea. We have no idea. Still having fun.
That is blasphemous, but it's not one of the blasphemies I mentioned, I don't think. No ideas? Is this guy that scary?
Oh, multiply with the conjugate, and then we carry on. No.
That just gives the radical at the bottom.
No, but we get rid of the radical at the bottom. But if you multiply with the conjugate, x minus square root of x.
Or
Yeah, but then we'd have that on the top, x minus square root of x, and we would have x squared minus x. Does that actually help us?
Then we divide with the highest power. No, never mind.
Just do use substitution.
I'm just.
What u sub would work?
You have u equals a radical of x. So you have 1 over x. I don't know. I really feel sorry.
Wolfram.
X plus square root.
That does work. So she redeems herself, but how do you know that you can make that work?
I was right.
Yeah, u equals radical x. U equals radical x is how we're going to do it, yeah.
Well, because when you find
1 over
U
c
squared could equal x.
because you can find 1x dx.
U squared will equal x, but we don't know how to do u x squared plus x either. What you have to worry about is the substitution will actually replace a function. Perhaps it's easier if I wrote it this way.
Factorize. What benefit?
Then your u would be
X.
radical x plus 1. So your du would be 1 over 2 radical x. X, or in other words, 2 du is going to be this 1 over radical x dx. Right? Which is this part. And so this would become what?
1 over u.
2 times the integral of 1 over u du,
ln.
which is 2 ln absolute value u plus c. So this is 2 ln 1 plus radical x plus c. So you can do that in Calc 1. ln is in the answer, but you know, it looked innocent enough. Let's move on. That's pretty much all I wanted to do for 5.3. So we have 5.2 and 5.3. Yeah, let's see if we can get through 5.4. Let's go quickly. 10 minutes. 10 minutes. 5.4.
If no homework, then sure.
Screw this. I'm just gonna get a projector and just talk through it. It's like 10 minutes. 3 homeworks. Okay, 5.4. Let's generalize these things. So 5.2 dealt with the natural log. 5.3 dealt with the natural exponential. What about general logs, general exponentials? How do we do calculus with those? General log and exponential functions. Which means, what if the base is not e? How do we make things work? Okay, and I wrote here, recall the laws of exponents, like x to the a times x to the b is x to the a plus b, blah, blah, blah. Pretend everyone knows that. So here's what we're going to do. Let a be greater than 0, be a constant. I'm going to use one of the log rules to my advantage. X is a real number. Then, it turns out, let's say I gave you a general function, a to the x. Could I rewrite that as a base e if I wanted to? I want to rewrite this as a number with the base e. Remember we had a rule that said something like, yes, e to the power of ln of a to the x. Right. So any number, I can do this manipulation, right? Just throw it in the power of e to the ln, and that will actually work, because these guys just cancel each other and gives you back that a to the x. So this is going to be that trick, how we're going to get these guys, transform them into someone we already know how to deal with. Right? So, or you can do this like e, by applying another log rule, you get e to the x ln a. Right? That's what we're going to be using to find the derivatives and integrals of general exponential functions. We're going to do the derivative of log functions, but we can't do the integral of log functions yet because we actually don't know how to integrate ln x yet. That we won't know how to do until like chapter 6. So, in other words, let's do a derivation. So if I wanted to derive, this means, if I wanted to derive a to the x, how do you think I'm going to do it? It's the same as differentiating e to the x ln a. How would I differentiate e to the x ln a?
X ln a e.
No.
Or differentiate the power.
You differentiate the power. What's the derivative of x times ln a?
1 over a.
It's just ln a, right? It's x times a constant because a is a constant. So ln of a is a constant, so it's just x times a constant. The derivative is just a constant times the original function. But what was the original function? It was just a to the x. So this gives us the rule for the derivative of a general exponential function. The derivative of a to the x is a to the x ln a. Or a greater than 0. Example. What is the derivative of 2 to the x? Or what is the derivative? Yep. 2 to the x, ln 2. That's it. Right? Notice that the same rule actually works if a is equal to e, right? E to the x, the derivative would be e to the x times ln of e, but ln of e is 1. Right? So it will still work out even if, so you can even memorize this rule instead of the e to the x rule and it would still be fine. Let's do something by the chain rule. What would we get? By the chain rule, what if I ask you what is the derivative of a to the u, where u is a function of x? A to the u times ln a times the derivative of u, right? It's u prime, right? That's what the chain rule says. Differentiate the outside, multiply by the derivative of the inside. So let's do a couple examples with that. For example, if I ask you what is the derivative of 5 to the x cubed? 3x squared times 5 to the x cubed times ln 5. So if you see something like this, do not do the power rule. Don't be like, oh, this is just x cubed minus 1. Power rule doesn't apply because the power is a variable. Okay. The base is a constant. You'd have to do something else. Okay, so we did that. Told you about the graphs again. Showed you how to sketch them. Maybe I'll do that next time. Let's do some integrals. And next time, reminder to talk about the graphs.
So 5.4 is not that.
What? No, we're not going to finish. There are just so many cool things to tell you. I can't. Okay, let's do. So let's say, what is the antiderivative of a to the x? How would we do it?
Antiderivative of e to the x.
Right, so you rewrite it in terms of something you already know, right? So this is e to the x ln a dx. What is that?
The same thing.
No, it's not the same thing.
ln a e to the power x ln a.
Nope.
Isn't the division of e equal to u? Oh, 1 over.
Don't forget the basic rules. If you have x times a constant, that's the antiderivative. What's the antiderivative here?
1 over ln a.
In other words, it's just going to be a to the x divided by ln a. So that's our rule. The antiderivative of a to the x is a to the x over ln a. Let's see. And this works if it doesn't work everywhere. It works if a is greater than 0, but it obviously can't be 1, right? Because what if your a is equal to 1?
You have natural log of 1, which is 0, and divide by 0.
Right, so how would I do that? What if a equals 1 here? What's that?
That's a itself. So just
No. It would just be 1 to the x, which is just the integral of 1, which is x. We know how to do it at 1. So we don't need this formula for being 1. Right? This formula will work in this range. Example, antiderivative of 3 to the x. We'll stop after this example. So next time we'll talk about the graph, some limits, and another shortcut to log differentiation. So you don't have to split things into pieces. Okay, this one should be quick.
3x over ln 3 plus
Okay, not much to do here. What about this one?
17.
U equals
x cubed plus 1.
x cubed plus 1. This means I have 1/3 times the integral of 5 to the u du, which is 1/3 times 5 to the u over ln 5. C, which gives us 5 to the x cubed. Let's write it. Gives us 5 to the x cubed plus 1 over 3 ln 5. Let's see. Questions? Boom! Oh my god! Alright, what do we do? I don't know, I'm stuck here. U equals x cubed plus x.
No, we need the 2x at the front to do that. Is your question?
U is x cubed plus s, and then you can, when you take the derivative, you can divide it out to be 2.
Yeah, but what's going to happen there? This side have to make u. So I'm going to have pi to the ln of u.
We factor out 6x squared plus 2 and substitute.
Factor out what?
The 6x squared.
Factor it out and put it where?
Outside.
You can't put it on the outside. There's an integral sign here. It has an x in it. And it's a dx. You can't move x's outside.
Go inside
Make ln x cubed plus x as u.
and then substitute x cubed plus 3.
U equals ln of x cubed plus 3x. So what would du be?
1 over
X cubed plus x.
3x squared plus 1.
3x squared plus 1 dx. Okay?
Then
Do you have that?
3x plus 1 goes to the other side and we substitute.
Huh?
Oh,
No, yeah, we just take out the 2 from the factor 2.
You can either factor out a 2 here, or you can multiply by 2 here. Either way, you're going to get the same thing. Just multiply both sides by 2. And look at that. You get rid of all of this.
so then just power to the
So then we only end up with
2 pi. And the 2 we
2
take out.
on the outside.
Yeah. 2 integrated
2 integral of
pi u.
pi to the u, du.
And
Pi to the u. How do we do pi to the u?
it's pi u over ln u.
Pi u over
ln pi.
ln pi times 2 plus c. So this would be 2 pi to the what power?
ln x cubed.
Was that super hard? Looks scary, right? You see that and I freak out, but it's not. That's what I'm trying to tell you. These things, they only look scary. Okay, we'll stop there. So homework for 5.2 and 5.3 due next class, and we'll pick up with the rest of 5.4.